My technical project is on tactile perception with autonomous control. To understand the need for my investigation, we need to first look at a specific problem in car manufacturing. Now, most of modern automobile manufacturing is done by robots. There is one aspect of this process that robots cannot currently do in an assembly line, and that is to figure out if what they did was correct or wrong. This part of the manufacturing process is called quality assurance, and it's mostly still done by humans. A team of highly skilled professionals are required to manually go and use their hands to find faults in the finishing of each car. The main thing that they look for are edge abnormalities, which, while they are doing it, they are required to wear gloves, which reduces their sensing capacity, but it's still good enough for doing the task. The reason why it's proved non-trivial to automate this task is because each robot we see here are programmed explicit instructions. They are not allowed, for example, to make any sort of decisions on their own, and thus even slight adjustment requires reprogramming by professionals. The promise of modern machine learning should, however, be able to help us here. If we are able to automate at least some part of this, we would save workers a lot of time and improve the overall efficiency of automobile manufacturing at large. Instinctively, you might think that the problem can be solved by machine vision. And you're exactly right, but after long and extensive studies, it proved non-trivial to use machine vision to solve this kind of edge detection. The type of edge and texture we are trying to detect are much more subtle, and we need more robust predictability. Physically speaking, using light sensors, we can only get two types of information: the time it takes for the light rays to be bounced back and the color of the surface. Most conventional algorithms that use machine vision to detect edges use this color information as an indicator of edge, making the important assumption that the color gradient is a function of surface geometry or angle. In our case, though, this assumption cannot be made because the surface we are dealing with is mostly homogeneous in color, and the edges create very small or no change in reflected color. Not to mention, it requires the light setting to be optimal. For this reason, we need a new form of physical data. The other problem with light is that when we are dealing with shapes that have angles of 90 or more than 90 degrees, even at optimal positioning, it would be physically impossible to detect the shape of the edges as light travels in straight lines. And what about situations where the light settings are not optimal? We cannot with any confidence be able to predict the existence of edges. An ambitious solution would be to use robots mounted with cameras at their end. This is exactly what we did. We mounted a camera at the end of an industrial arm, but rather than just have a camera making observations, a better approach would be to make this camera record some interactions with the surface that would reveal more information about the surface and give us new physical data rather than just color. If that doesn't sound like a light sensor, you're absolutely right. It's a tactile sensor that uses a webcam to record the data. Now, the design of this tactile sensor is key to our solution. The way it works is it uses a 3D rubber sphere dotted with regularized pins enclosed by a gel with LED lights and a webcam. The pins are modeled based on the surface of the human finger and how we ourselves use the topography of our fingers to detect surfaces. The LED light illuminates the surface of the sphere while we use the webcam to record the data. Our design has the added advantage of being significantly cheaper than a lot of commercial ones which use expensive electrical components rather than pins. Also, unlike humans wearing gloves, our sensors will be able to resolve greater detail. Another reason why this tactile sensor is interesting to use is that we can learn a lot about how things like fingerprints are useful for detecting surface textures in animals and humans, which, by the way, is still an open question, and how our brain would and how our brain would interpret data from it. For this project, I have been given access to an ABB IRL series robot and the Tactile sensor. One of the first tasks I had to do was to provide a solution to get data off the webcam remotely. The second and much more intensive task was programming the robot, which has been a major part of the project as there is no software solution in place to create an open or closed loop controller with the robot. We cannot get data off our Tactile sensors if we are unable to have a real-time controller for the ABB robot. The reason it needs to be soft real-time is because the data we are acquiring from the Tactile would be a time series data, and applying the Tactile to the surface will result in real-time deformation, which is a function of both time and impulse. We do not have direct access to the motors and actuators for the robot. We have only access to a controller the robot is connected to. We cannot also directly send positional or rotational information data to the controller. It should be noted that the rotational information is encoded using quaternions. The controller needs to be connected to the LAN, and we will only be able to send commands to the controller via TCP/IP sockets, which also we do not have direct access to. The controller can only execute rapid code. Rapid is a domain-specific language for controlling ABB robots. ABB has provided us with an C# SDK so that we can develop the required software tools for our project. We can then use C# to directly send commands to the robot, which then executes specific subroutines and solves the inverse kinematic problem for us to move the robot to the desired location. I had to create a significant non-trivial software solution to robustly allow MATLAB to directly control the robot. No one at the lab has been for years been able to control these expensive robots, and the robots have been just laying there and not doing any important experiments. Significant interest has been shown to use my solution to allow other researchers and academics who have mostly written their algorithms in MATLAB to use the robots to run their experiments. Some specific problems I had to deal with was related to network programming and involved concurrent race conditioning. The main goal of our project from an application perspective is to detect edges and gaps at the minimum. We also would need to map that information onto an appropriate coordinate system. There has been some studies done on how to process the data. However, we are unable to adopt these techniques due to the fact that the sensors we are using are not the conventional sensor that is used for tactile perception. My plan is to use an Bayesian classifier as a first approximation for the decision algorithm. The little research that has been done on these sensors tells us that any parametric or analytical technique will not give us good classification. One important aspect that requires study when it comes to the classifier is feature selection. Our first approximation was to use luminosity from the webcam feed and use histograms, but there is a better novel technique given the type of sensor. Rather, we could track each of the individual pins on the surface. To do this, however, we first need to identify the position of our pins. We're able to apply a blob detection algorithm first to detect each of our individual pins and then track them in time. The assumption is that the blobs do not move much from their initial positions at each frame. We are using a modified version of the Lucas-Kennedy algorithm used for optical flow for tracking each of our pins. We can then greatly reduce the dimensionality of the data set that we pass into our classifier. In this case, it would be the positions of each pin in time. Active perception is the ability of the robot to understand the validity of the data it's collecting. Simply put, if the robot thinks that it hasn't collected enough data, it will go ahead and collect some more data in a way to maximize the predictability of the classifier. It also means that the robot can also sense if it needs little or no data to make predictions over a given surface. The robot would, for example, prioritize following an edge that it might have detected and follow the contour of the edge. This would, by orders of magnitude, reduce the time for the robot to map all the edges on a surface, and also at the same time give us highly resolved edge maps. This type of nonlinear autonomous control is crucial if our tactile sensor is to be useful in doing the task it's given before the end of the universe. For doing this project, I had to spend my entire Mondays at the Bristol Robotics Laboratory. I've taken a few videos to show the progress that I have made this far. This clip shows the industrial arm making 20 taps on a curved surface and returning back to its original position. The robot is an expensive and dangerous piece of hardware, and so I had to use an application called RoboStudio to run trial simulations to make sure my code would not kill me or my supervisor. This video shows the full setup that has been created. On the laptop on the left, you can see the blob tracking algorithm in soft real time. And on the right, I'm running a closed loop asynchronous controller for the robot. The frame rate is about 12 frames per second, which is not the best rate we would want. The reason for it is because we did not anticipate the calculation would take such a long time. In the future, we will use a concurrency model to scale up the maximum allowed frame rate of the webcam. The project tries to solve a very specific problem in a specific industry. But my hunch is that if the project can be completed with positive results, the solution could be applied to edge detection using tactile sensor much more generally. Even if the results are not positive, the testing and experimenting framework that was required to conduct this project would be useful to other researchers and academics as well. We have approached this problem from a very practical direction, rather than thinking about the problem in abstract, where we might trade usefulness for mathematical elegance. We therefore will also be able to test a lot of promised learning algorithms in the real world. As Richard Feynman once said, the test of all knowledge is experiment. Experiment is the sole judge of scientific truth. Thank you for your time.